Hello, I'm Thomas Olson. I'm doing a video on the Mandelbrot set. It's going to be a longer than usual video. I have made this video already, but I wasn't really happy with the result. I think I could do better. The main thing I want to drive home is that the Mandelbrot set is an angle multiplication plus vector addition, and it's reiterated. I'll go over that. Alright, so what is the Mandelbrot set? So this here is Khan Academy, and they have a wonderful JavaScript tutorial, programming guide, whatever. And on here we can just do JavaScript, but it's not regular JavaScript because they had to make this platform work. So I mean, you can make this. You can delete a couple of these semicolons, and I think it worked fine in a regular, maybe. I don't know. On a regular web page. Anyways, let's forget about that. So this black stuff here is the Mandelbrot set. What I can do here is I can comment out these things right here. This is the color functions, and so that there, everything you see is the Mandelbrot set, but we can't zoom in because this function overwrites what's already there. It just makes a mess. So let's go back to the first one here. So that's the Mandelbrot set. What most people want to learn is about these colors. Now if you look at this, I made a mistake here. Well, it's not really a mistake. I'm going to go to 100 iterations, 180 iterations, and I don't quite know what Exasier is doing here. Like, I took this code from him. I just showed you that. Right here is the original person that made this, the original code. So I edited that. It's 180. When you do a circle, when you plot a circle, you go from 0 to 2 pi. So I can do 360 right here. 0 to 360, which is 2 pi. And well, I don't know if your computer can handle it, but mine can't. I'll crash pretty quick. Or not. Okay, I made it to the bottom. It worked fine. So these colors, they got a wave thing going on. I want to show you that. But for this tutorial, I'm going to go to 180. I don't want to go through a bunch of crashes. Okay, here is your primary function. Let's turn this back into the regular Mandelbrot set. Alright, so we got x1 times x1 minus y1 times y1, y1 squared, x squared minus y squared, and we can do x0 right here. So this here is the angle multiplication. This here is the vector addition. All right, 2 times x1 times y1 plus y0. And there we go, Mandelbrot set as you know it. Now, I kind of like vector subtraction better. If you go to here, vector addition, in vector addition, the vector you're adding ends up being u minus v. We'll go over that right now. So what we need here is plots, so I can use the arrow. There might be a better way to do this, I don't know. I would prefer to have no arrow, just the legs, line segments, but we got the arrow. It'll do. Okay, so we can get rid of that with the colon, and so this would be vector addition, but let's get the vectors in play first. Okay, now that's wrong. Now we can put this vector onto this right here. And then we could put the other vector on top. So what I'm doing here is I'm just moving the origin point around. Now the vector addition would be this vector right here. So okay, and there you go, that's vector addition. Now, what I like about vector subtraction is instead of this mess coming about, what you do is you have that vector right there and that vector right there, and you just join these two. It's vector subtraction is this vector right here, and say if you wanted to know the distance between two particular angles on an n-gon, that's kind of fun to do, like a 5-gon. You wanted to know that distance, so you could just do I don't know, some weird geometry stuff, but yeah, if you do vector subtraction and do the distance on the vector, and you can get that length. I think that's the only particular number I want. I haven't seen very many instances where this vector, this particular vector was needed. I've only seen it where this vector was needed. So So here is the 3, 4 vector. And oh, I messed that up. So that's vector subtraction right there. Anyway, this particular vector is actually double the -7, 24 is double the angle of 3 and 4. If I were to put those into this here, cos of alpha would be 3. So 3 here, 3 here, -4 here, -4 here. And I do the same thing to this vector. And what we have here is alpha plus alpha. The difference here specifically would be that I'm doing math outside the unit circle. These are all, this cos here is a unit vector. It's cos and sine, they're unit vectors when they're used like that. I mean, if I were to put a 2 right here and a 2 right here, they would not be unit vectors. So if you were to put an x here, an x here, a negative y here, negative y here, and to multiply that vector by itself multiple times, you get this n times x and n times x right here. And if there were unit vectors, you could just plant it in, but you don't need to be unit vectors. It could be x, just regular x right here, regular y. This k here would still have to remain, and then minus k. Here's an ellipse version of the same thing. So this part of the function, really what we're doing is multiplying by 1 or 0, and if it's 0, the current term that they're in gets thrown out. So this here is pretty much exactly the same function as this part right here, and this is exactly the same. It's a sum from 0 to n, sum from 0 to n, and this function, it's just picking 1s and 0s. It's the same thing essentially as this, but it's different 1s and 0s. I suppose you can make sequences and you can put one root here and another root here, and you can divide it by the discriminant. I suppose that'll work, and you make weird sequences, but when I entered them into this function here, and I'm doing the same stuff, it just makes wonky stuff. If there's something to this, I can't figure it out. There just seems to be two functions that get rid of two root functions that seem to get rid of stuff. I'm not really going to go into that. You can look at roots and figure that out. It's not too hard. So I want to look at the waves next. So we got this blue colored here, and we come down here. We got the blue colored again. That's 2. That's 3. Okay, that wasn't good. All right, 1. 2, 3, 4, 5, 6, 7. Okay, I counted 1 twice by accident. It's supposed to be 6. Do you know how I know it's supposed to be 6? No, it's supposed to be 7. My mistake. That is 7. So we got 14 here. 14 divided by 2 is 7. And we did 180 degrees. That's pi. So this here is 14 times pi. And a circle is actually 2 pi. So there we go. We could change it to 12, and we'll get 6 color variations. Now there's a lot of people that put all kinds of weird functions in here. I'm using the spherical function. This here is the first one. The sphere, when you have 2 variables, it's usually, this one would be a theta times theta, and right here would be phi here, phi there. And if you do the square root on this square plus this square is equal to 1 times that, so it ends up being the circle, cos and sine on here. That's how you do the sphere. Now I suppose you can change these. You can give this a funny number right here, 5, and see what happens. I don't think you can count them, but well, it's some pretty nice color functions going on. So let's count our 12. We're expecting 6 color variations. Baby blue here. We'll come down here. 1. There's 2. Let's go into here. So we're coming in. There's 3. Let's come into here. That's 4. You know, it's easier to count them when we jump into these things, so let's just keep doing that. So we're at 4. that's 5, and that's 6, and that's the end of it. So 6, and right here would be the color, the last color that we get to see, and that would be the color just before baby blue. So if we went over here, it would be baby blue. We can zoom out. I don't know if it'll, there we go. So I'm right clicking to zoom out. So there's a wave function happening here, and it's pretty interesting. And when it gets back, and when it gets to the end, it just kind of, well, it just kind of rounds off. So what I want to get to this part next. So we can do vector subtraction. What we'd have to do is subtract both of them, and that just reflects it to the other side. I suppose we can do the same thing over here and just manipulate it that way. Yeah, I have no idea what I just did there. That's kind of cool though. No, that's not cool. Yeah, this is reflection kind of stuff going on. Anyway, we do not have to do x0 right here. We could do that. Put ones, zeros, change the ones to zeros. We can copy this, do the exact same thing. And this here looks exactly like the logarithmic one. So I'm made a log logistic map, I should say. Now, if you look at these two, they're exactly the same. I mean, it's a little wonky right here. If you remove the colors, they're exactly the same. With the logistic map, to get it like this, I had to start with an initial value of 1/2 for x1. So I suppose you can start x1 and you can get different results. I'm not really happy with that, to be honest. So what we did was we repeated this function, but we put zeros, and we got the logistic map almost. Logistic map's all wonky. Look at this. This top part here is higher than this top part here. So I don't know what to say about that. There are lots of videos on the logistic map and all this stuff going on. I'm not really gonna go into that. So as for these functions right here, I will get you to look at right back at the rotation matrix. So that there is the rotation matrix, except it's not unit vectors. And right here, x squared minus y squared. I mean, we could put x1 here if that makes you happy. X1 squared minus y1 squared. And if you do 3, so alright, the problem we have here is that JavaScript can't see x squared like that, so that's why I've been putting x squared, that's why I've been doing that essentially this whole time. All right. Alright, so what we have here is the third one times the second one. This is the one we started with. I know this because of this right here. We can also goof around with this. Let's see if we subtract it. It should be exactly the same. It isn't there because you have to subtract both of them. So it just reflected and they're exactly the same. But you can change these two around. Okay. That wasn't exciting at all. And if you count them, you still got the same exact thing going on. You count the same amount of waves. So right here is the length of the vector. It's the magnitude squared. We can do a square root right here. The problem with that is that it'll take too much resources. So we do the square to the magnitude rather than just the magnitude. And this, see, it'd be square root. We square it. It just doesn't have the squared in there. What we can also do is switch to we can switch to the area, like I said. So we're adding these two vectors. We're doing vector addition. Let's switch back to addition. All right. Now instead of the magnitude, we want the area between here. So to do the area, we need to get the determinant. Alright, so we want the determinant between x1, y1 and x0 and y0. So we do this, and we got ourselves a little bit of problem. Why do you think this is happening, do you wonder? Well, what we could do is we need to make another, we need to repeat it. And that there is way too big. We need a smaller area. Let's try 56. Let's try 6. All right, I think we have ourselves a bug. This here is less than 4. The area is greater than -4. That sounds right. Okay, that looks like a bug. That is not how it should look. Now I did this previously on a different one. Here's an area one that worked. My computer has a lot of programs loaded up. So that's probably what's going on here. I made a value area and I put it in there. Now this is a different color function. I'm not gonna comment on that. I'm just gonna let you make your own jokes. With the area, it makes these shapes. See, this here is Xacier's color function. Oh no, this is my function. I just used 7 and 8 right here. So it's 360 and I didn't crash. That's good. Put 7 in here. And there's this logarithmic function. I don't know what's going on with the logarithmic function. I haven't really looked at it that hard. I don't think these round things are where it's coming from. Let's get rid of it and just do this. So we got, maybe we need to go increase our area a bit. That looks a little bit better. 6. No. I wonder if there's a value here that's best. That kind of looks like it's pointed. It's 16 maybe. That looks better. Maybe not. Okay. Alright, anyway, we could still count these things and we get exactly how many we think we would get. Alright, so I went over colors area. I don't think there's very much else for me to go over. Oh, I want to change gears here, and there's the Mandelbrot. So if you didn't know that it was an angle multiplier plus a vector addition, you would not be able to step up to the Mandelbrot. I mean, if I started focusing on the Mandelbrot 10 years ago, could have been me that figured this out, but I mean, I figured this out independently just because I started buggering around with this stuff. So you see, you have your vector addition right here, just a regular vector. You can goof around here and put x 0 squared minus y 0 squared minus z 0 squared, the way I was doing with this stuff. Oh, this is the ellipse. So I've never done this before. This is wrong. It's probably going to get something weird. Oh, we got to go 0. Okay. So we have an ellipse thing plus a circle thing. And we got all kinds of wonkiness here. That's pretty cool. We got... I almost said it. But anyway, it's the exact same thing. I mean, I was kind of expecting a mess. It's just squished. That's pretty cool. So we're at the Mandelbrot, and like, this is just angle multiplication. Okay, well, watch this. All right. So like I said, that there is essentially the rotation matrix. Now, what if you want 3 variables? All right, x squared minus y squared minus z squared. X squared minus y squared minus z squared plus x0. That's the vector addition. All right. Oh no, we got something weird here. What the hell is that? Well, this here is the distance. We got the distance between y squared plus z squared. So that's the distance between those two vectors. What if we put 2 times x times y and 2 times x times z? So we split this thing here into 2 vectors. So that's one of the cooler things. I mean, we're trying to see higher dimensions and all that crap, but most people don't seem to get this. It's just the distance here. I mean, we don't really need complex analysis. We don't need the 4-dimensional stuff. I can't remember what it's called. I mean, I always know what it's called. It's just, this is one of those weird times where I don't know what it's called. I just not think about it. So we can do this with a third. This vector here, y, z, and I mean, you change these around, and that's exactly it. But you don't need to do any fancy math. You just use this matrix right here to find that out. And while I'm here, I'm going to show you the sphere function. So here is the sphere in R3. You should all be, I mean, this is where they study all by itself. I mean, it's pretty fascinating when you look at the patterns in here. Let's dial the patterns down to, I don't know, let's do 4. So you kind of see a thing going on here. Patterns emerging. That's the R3 sphere. Now, I suppose you want to see this sphere right here. All right. Actually, let's not do the sphere. Let's do the non-unit vector version of this. We get something surprising too. Yeah, so it's not a unit vector. It doesn't go between 0 and 1. So to put this into the sphere, we'd have to divide it by yeah, we'd have to divide it by that. So we're in the sphere again, and we got something going on. Alright, this is the second one. It's a little less fascinating, a little less interesting. Or maybe some people think that's more interesting. I don't know. Hard to say. And now let's put it into the sphere. So this would be just x squared plus y squared plus z squared. Doesn't really need anything, a square root in there or anything. That'll do. Now, I think I've seen this, people would do complex maps and this little bubble thing would happen. And since it's like a double angle function sort of thing, it's a two-dimensional angle function. So from the two-dimensional perspective, it's doubling the angle. It would be on the same plane in some angle on the sphere. Like if you multiplied some vector, if you just made 3, 4, 5 and just kept on incrementing this right here, it would be on a plane and it would just keep going around. Yeah, there's something else I forgot to show you. No, sequence right here, and what we want is, oh, there's too much setup for that. Yeah, I'm not going to set that up. Alright, so you have Mandelbulb. You have an idea of the Mandelbrot. I'm not a three-dimensional programmer. I mean, I would like to get into that and make my own Mandelbulbs, but there you go. I showed you how to make some cool Mandelbulbs that no one's ever done before. There's no reason you can't do that, and I don't know. Yeah, no one will have seen them, and plus you can mess around with the sphere and do these kind of color variations. There is a limitation on this. I think the sphere function here, it doesn't do the spectrum quite as nicely, because I think there's an aspect of the color waves that's brightness or something that's impacting the look. I could be wrong. I don't know enough about that stuff. Anyway, I think that's good enough for now.